Hello, I'm the Mystical Mr. Daycock, and today I am going to be teaching you about recurrence relations. Now, recurrence relations relate to sequences. So let's take a pretty basic sequence: 1, 5, 9, 13, 17, 21. Now, this sequence, it goes up in fours, and you may be familiar with what we call the closed form of it, or the nth term form of it. If I call this U1, U2, U3, U4, U5, and U6, then our UN, i.e. the nth term, is going to be equal to, well, it's going to be 4n because it's going up in fours, minus 3. And this is our closed form. And we can test that this works. We can plug in a value. What if n equals 4? Well, then we're saying that u of 4 is equal to 4 times 4 minus 3, which absolutely is 13. And so you can see the u4 up here absolutely matches what we get when we look for u4 in our sequence. Now, recurrence relations are another way of doing with this. They are a method of considering sequences in a way that you probably more naturally do. Because what do we think about this sequence when we first see it? We think, oh, plus 4. Oh, plus 4. Oh, plus 4. We're going up in fours. And that's what a recurrence relation does. What it says is if we take our term un and then we add 4 to it, well, that should give us our next term. But if we're dealing with un, the next term is un plus 1. And that's a recurrence relation. It represents this sequence not by thinking about a particular point of the sequence, but by thinking how each term connects to every other term. So in this case, this sequence, each term is 4 more than the previous one. But that's not quite the whole story, because there are lots of sequences like that. We could consider the sequence 2, 6, 10. This also goes up in fours. 0, 4, 8 also goes up in fours. Or 4, 8, 12 also goes up in fours. Where the nth term can only have one sequence, when we write down a recurrence relation like this, it can have multiple options. And so to define it, we also need to say, let u1, which is our very first term, and we almost always pick the first term, but we don't need necessarily, we can pick various different options, any term will work, but we just need to give enough information to define it uniquely. So we add that, and now, because we've said what our first term is, there is only one possible sequence. It is this one sequence up here. So this whole thing in the box together is our information to define the original sequence. And again, we can test it out. Let's see what happens if I put in u5. So if I say n equals 5, so we're dealing with the sequence un plus 1 is equal to un plus 4. I'm going to put in n equals 5. Let's see what happens. And I get n plus 1. n plus 1, if n is 5, is 6. So I get u6 is equal to u5 plus 4. And so what it's saying is the sixth term is the fifth term plus 4. And if we go up, we can check that and go, yeah, absolutely, the sixth term really is the fifth term plus 4. But notice that that doesn't tell us anything about the fifth and sixth term unless we already have some information about what numbers are involved. And so that is why this bit on the end is vitally important for a recurrence relation. Otherwise, it doesn't make any sense. Now, let's look at a real-world example. John opens a savings account with £1,000. The account gives 3% interest a year, and after interest each year, John invests another £300. Write a recurrence relation that satisfies this information. So, what we need to do is consider what's going on. So we want to think about how much money we have after the nth year. So we're going to ask ourselves, UN, this is the nth year. And what's going to happen to that? We need to, because again, the recurrence relations are about how things relate to each other, not about the individual specific term. We just want to see how it connects. What do we have to do to our term to get to the next one? Well, the account gives 3% interest a year. So that tells us we're going to have to multiply by 1.03. That's how we get 3% a year. And then also, John invests another £300, so it tells us we're going to have to add 300. So our recurrence relation, what we have to do to the nth term is 1.03 times by UN, and then add 300 on the end. And what will that give us? Well, it will give us the next term. It will give us the next year's amount of money. And so it will give us UN plus 1. So UN plus 1 is going to be equal to 1.03 UN plus 300. But that's not quite enough, because at this point, if someone just saw that, they'd be asking, well, what is UN? So we also need to write at the end what we're talking about. Or in fact, arguably, we want to write that beforehand. But we're going to say, let UN be the amount of money sorry, I can't spell money there, in the account in pounds. We need to say what unit it's in, because if it was in pence, we'd be dealing with entirely different numbers here. In pounds after n years. And now we're done, apart from one specific piece of information, and if you were paying attention, you know what that is. We need to give a starting point. And what's our starting point? Well, that's the £1,000 here. Notice that that wasn't included. We didn't use the £1,000 anywhere here, because this was just about how one term connects to another. The £1,000 comes in as our starting point, and how many years have passed at that point? Well, 0 years. So that's got to be our U0, not our U1. You also write down that U0 is equal to 1,000. And this here, including the definition, is our full description of that information in a more mathematical sense. Okay. Speaking of mathematical things, let's deal with a more mathematical situation, because recurrence relations are often just done for fun by mathematicians. So we'll take a very famous one, the Fibonacci sequence: 1, 1, 2, 3, 5, 8, and 13. Now what's special about this is that each term, so the 2, is the 2 terms before it added together. And the 3 is going to be the 1 and the 2 added together. Oh, I wrote multiply. I've written multiply both times. Added together. And the 5 is the 2 plus the 3 added together. And that there defines the Fibonacci sequence. And with that in mind, we can write a recurrence relation for it. If we're going to be dealing, if we're asking ourselves what is our nth term, so what is UN? Well, UN is going to be equal to the previous 2 terms. Well, if we're dealing with UN as the term we care about, the term before is UN minus 1. But that's not enough. We also need the term before that, which means we also need to include UN minus 2. And this defines the Fibonacci sequence, except, again, as always, we need our starting point. So our starting point here would be that we need to deal with U1 equal to 1. But that's not quite enough information in this case. Because our nth term is dealing with 2 different terms, we actually need to start with both the 1 and the 1 before we can get to the next sequence. So because this is what's called a second order recurrence relation, we also need to include that U2 also equals 1. And that is our full information. Now, sometimes you might be given an equation. In fact, we want to necessarily prove that two things are related. So let's consider our original example where we had our nth term form was equal to 4n minus 3 and our recurrence relation was un plus 1 was equal to un minus 3. No, not minus 3, plus 4. And we want to show that those are actually the same thing. Well, to do that, we need to consider both the left-hand side and the right-hand side and see what happens when we plug in this sequence. Let's check if these are actually representing the same thing. So on the right-hand side, it's pretty easy because we're just going to get 4n minus 3 plus 4. And what does that become? Well, that gives us 4n plus 1. That's the right-hand side. On the left-hand side, we're dealing with something different. What is un plus 1? Well, it's going to be un, but with n plus 1 instead of n. So that's going to be 4 lots of n plus 1. So our left-hand side is 4n plus 1 minus 3. Let's expand that out. We get 4n plus 4 minus 3, which is absolutely 4n plus 1. And so we can say that the left-hand side is equal to the right-hand side. So un equal to 4n minus 3 satisfies the recurrence relation un plus 1 equal to un plus 4. Okay, and that's all I've got on recurrence relations for today. I am planning on doing a couple more videos on this, so if you want to learn about how to find a closed form given a recurrence relation, tune in for the next few videos. Thank you very much. See you next time.